This is lecture 4 in sugar, and today we're going to be talking about disaccharides. All right. So we saw last lecture that reactions of monosaccharide hemiacetal with an alcohol gives glycosides. In your notes from last lecture, you should have this, where you have a hemiacetal sugar. And when you react with an alcohol, you get an acetal, and we call this glycoside. Now we're going to use that same exact chemistry in which the OR group onto a monosaccharide, giving it an acetal, instead of using just a regular alcohol like methanol, ethanol, we're going to use another unit of a monosaccharide. And when you do that, what you get is two monosaccharides connected together called disaccharide. All right, so here's a structure of such chemistry, and what you're seeing is you have a monosaccharide reacting with another monosaccharide. So one of them is going to serve as your hemiacetal. So let's say that the left sugar is going to serve as our hemiacetal, and the anomeric carbon, which is right here, is going to be the one that's going to be replaced. This OH is going to leave as water, OH2, and then in its place, one of these OH groups from the second monosaccharide is going to replace that water, right? So think of this as your hemiacetal, and think of this as your alcohol source, right? So one question that it might pop into your head is, which of the OHs that you have is going to connect with this anomeric carbon of the hemiacetal? So it turns out in nature, the C4 of the second monosaccharide. So this is carbon 1, carbon 2, carbon 3, carbon 4. So most commonly, C4 alcohol is the one that replaces. So you could think of this whole thing as an R group, and that replaces the OH. Or in certain cases, for example, in glycogen, you see the C6OH. Doing that same job. All right, so what happens, I'm going to just blow it up so you can see it better. So what happens is that you have a linkage happening in here, and you know that at C1 of the hemiacetal sugar, that this could exist either up or down, right? So when the C4 alcohol of the second monosaccharide comes in and makes the linkage, which is right here, that's the bond that is formed between the two sugars, two monosaccharides. This could be either up or in the same area as the CH2OH, causing that to be the beta glycoside linkage. All right, or it could be down, as in this picture right here, called the alpha glycoside. All right, so two formations are possible just because you know that at this carbon is constantly opening up and closing anyway. All right, so to name the glycoside linkage, this is carbon 1 of the hemiacetal sugar, and remember this is carbon 4. So the notation is that the glycoside bond is between carbon 1 and carbon 4 and is a beta glycoside, whereas in this one is 1 to 4, but is an alpha glycoside. All right, so when you look at the disaccharides, note that at this bond right here at the anomeric carbon is not going to open up and close, because this is now at an acetal stage, right? Because you got 1 OR and 2 OR. So this is stable, not going to open up or close. But at this carbon, this anomeric carbon, this is at the hemiacetal stage still. So at this carbon, it's going to open up and close again. All right, so the same chemistry that you've seen before is going to still happen with this unit of monosaccharide. So in essence, I'm just going to draw a very crude drawing of what it would look like. So if we have the first sugar that's in the acetal stage, I'm not going to draw in all the OHs so that you can really focus on the carbons that are important. So if you have this, where this doesn't open up, but notice in the second monosaccharide, it will open up and close. So I'm going to draw that. So then you're going to have the aldehyde at this anomeric carbon opening up and closing. So in aqueous solution, if you have this 1,2,4 beta glucoside at this anomeric carbon, this could be this is going to be a mixture of alpha and the beta, along with the opened up form, that looks like this. So what does that mean in terms of chemistry? The same chemistry will happen. In other words, the disaccharide that has hemiacetal will still be able to be reducing sugar, and it will still mutarotate. So those chemistry that you learn for monosaccharide will still apply. All right. So that's kind of an overview of how the disaccharides form and what the chemistry would look like. What we're going to do now is look at specific disaccharides and go over them individually. All right. So rather than have you memorize the structures of all disaccharides, what I want you to be able to do is this. This is your goal. Memorize the names of the two monosaccharides that make up the common disaccharides. So we're going to look at lactose, maltose, cellobiose, and sucrose. So if somebody asked you, what is sucrose? You should be able to name, answer back saying that is a disaccharide. And it's made up of glucose and a fructose, for example. Okay? And that's the at the extent that I want you to be able to do. What is the difference between maltose and cellobiose? We're going to go over that in a minute. So these two questions you should be able to answer at the end of this lecture. All right, so let's go down to the maltose and cellobiose, which is the most commonly found disaccharide in nature. And both maltose and cellobiose, believe it or not, even though they have different names, is made up of same two monosaccharide. That is glucose with the glucose. So this is what happens to food when you eat starch. Starch is a polysaccharide of glucose, and when you break it down, you get maltose, which is a disaccharide of glucose, which is then further metabolized down to two molecules of glucose. But cellobiose, which is basically same thing, made up of 2 units of glucose, is also a product when you take a cellulose, which is a polysaccharide of glucose, and break it down. But you know from your experience that we could eat starch, but we can't eat cellulose. All right, if they're both made out of glucose, why could we eat starch, but why can't we eat cellulose? All right, because of when you look at those two disaccharides carefully, you should note that the maltose, the linkage, the glycoside linkage is 1 to 4, as we saw before, is alpha linkage, and so the starch breaks down to maltose because we have enzyme that is able to recognize the alpha glycoside linkages, whereas in cellulobios, notice the linkage is beta. So 1 to 4 beta. And this is what you get when you break down cellulose. And we don't have an enzyme that breaks cellulose down. Our enzyme does not recognize the beta glycoside linkage. So isn't this amazing that only one bond makes a difference in whether or not something that is so closely related in structure, it could serve as a food or not. All right, and if there's a way for us to be able to digest cellulose by being able to break it down, these 1 to 4 beta bonds, then I think the food problem will not exist, because there's so much cellulose out there in the world. All right, so next disaccharide that we're going to look at is lactose. And you know what? I am going to probably run out of time before I finish lactose. So I'm just going to finish going over this. So in chemistry wise, if a question asks, is maltose or cellulobios reducing sugar, then notice the anomeric carbon here is ready to be opened up and closed. So yes, it's a reducing sugar. And is it going to mutarotate? Yes, because it's going to open up and close at this carbon, not this carbon, this carbon. All right. Another thing that is confusing to students is when something is called maltose, this 1 to 4 alpha bond is fixed. You don't change that. All right. So this whole structure is called maltose, and it's understood that the 1 to 4 bond is an alpha bond. All right. But you could have an alpha maltose or a beta maltose, and that's referring to this anomeric carbon, which could be, that's why it's in a squiggly line, it could be up or down, right? So if it's down, it's going to be alpha maltose. If it's up, it's going to be beta maltose. And in solution, you're going to have mixture of alpha maltose and beta maltose, along with a very small amount of opened up form of this. All right, so a mixture will exist, which is why it's mutarotating, and which is why you could that carbon could be oxidized. Same thing with cellulobios. You have alpha cellulobios and a beta cellulobios in equilibrium with the opened up form of this monosaccharide. All right. So after we finish the lactose and sucrose in the next lecture, you should be able to do 24.39.